What if the entire tech industry is basically trying to build a better light bulb by just, setting bigger and bigger fires?
That is exactly what it feels like right now, yeah.
I mean, when you look at the headlines today about scaling artificial intelligence or building the next generation of global networks, the solution always just seems to be brute force.
Right, more compute, more power.
Exactly. We're told we need data centers the size of small cities. We need billions of gallons of water just for the cooling systems, and millions of specialized silicon chips.
Not to mention dedicated nuclear power plants just to generate the absolute ocean of electricity required to perform all this endless power-hungry floating point math.
Right. It's wild.
It really is the defining engineering bottleneck of our era. I mean, the underlying assumption across almost all the major tech companies is that massive, exponentially growing resource consumption
Yeah.
is just, well, it's the unavoidable cost of doing business if we want more capable computing.
The whole paradigm is just raw scale.
Yeah, exactly. If you want a smarter model, you build a bigger fire.
But today, we are looking at a completely different blueprint. What if that entire foundational approach, like the basic arithmetic we use to build AI and distributed systems, what if it's just structurally wrong?
Which is a massive question to ask.
It is. What if the secret to infinite scaling doesn't lie in pouring concrete for bigger power plants, but in rethinking the absolute bedrock of computer science using ancient mathematics?
Yeah.
Specifically, what if the answer has been hiding in prime numbers and the golden ratio?
Which completely upends all the conventional wisdom. We're talking about abandoning the fundamental math that has driven neural networks for the past decade, basically, and replacing it with something entirely different.
And that is our exact mission for this deep dive. So we're unpacking a staggering stack of highly technical architectural notes, roadmap documents, and theoretical papers today.
There's a lot to get through.
There really is. And they all outline something called the Shannon prime lattice and the prime power transformer. And I mean, the claim here is not minor. They aren't proposing some software patch to make things 2% faster.
No, not at all.
They are proposing a complete rewrite of 6 distinct layers of computing.
Right. Starting from the microscopic logic gates on a silicon chip processing the data, all the way up through the memory management, the network routing, and finally to the global blockchain consensus layer.
And the promised result of this massive rewrite is what really grabbed my attention, because they claim they can get exact bit-identical outputs compared to standard state-of-the-art models, but achieving those outputs using just a microscopic fraction of the memory and compute.
Bit identical. That's the key word there.
Right. So whether you are trying to catch up on the absolute bleeding edge of AI architecture, or you're just intensely curious about how the internet itself could be completely rewired to escape this thermodynamic wall we're hitting, you're going to want to stick around for this. We're going to break it down piece by piece.
Absolutely. But to truly understand, we have to start at the bedrock substrate.
The math layer.
Exactly. Before we can even touch how a prime power transformer behaves, or how this network routes data across the globe, we have to unpack the foundational mathematical arena they're operating in. Because they have entirely replaced the way the computer, well, thinks about numbers.
Okay, let's start there, because this is where I hit my first major hurdle when reading the sources. Normally, AI relies on matrix multiplication, right?
Yep, standard dense matrices.
Like, if I want an AI to understand language, it takes words, turns them into huge grids of continuous decimal numbers, floating point numbers, and then multiplies those massive matrices together millions of times a second to find statistical relationships.
Standard neural networks are entirely dependent on that continuous floating point math. They use 16-bit or 32-bit decimals to capture the really tiny nuanced probabilities of how concepts relate to one another.
Right.
But the Shannon prime architecture completely discards continuous matrices. Instead, it moves all computation into a discrete mathematical space called a negacyclic cyclotomic ring.
A negacyclic cyclotomic ring.
Yeah, often denoted in the literature as R sub Q.
Okay, wait, I need to push back on this immediately. Standard models use those highly precise floating point decimals for a really good reason.
Sure.
If the AI needs to capture the incredibly subtle difference between the word bank as in a river, and bank, as in a financial institution, it uses the long tail of those decimals to represent that nuanced probability.
That's the standard thinking, yeah.
Right. So if you force all of that into a closed ring of whole integers, aren't you literally throwing away the data? How do you not lose the granular resolution of the AI's understanding?
That is the intuitive counterargument, definitely. But it kind of misunderstands what floating point precision is actually doing in high-dimensional space.
How so?
Well, the trailing decimals in standard AI models often represent false precision. It's basically computational noise that the network actually has to learn to ignore over time. The negacyclic ring doesn't lose the nuance. It captures the nuance structurally rather than through, decimal exhaustion.
Structurally. Okay, explain what you mean by that. Give me a physical sense of this negacyclic ring.
Okay, picture a closed circular track, sort of like a clock face.
Okay, got it.
You start at 0 at the top, and you have discrete integer notches around the edge. Now, in a standard linear number line, you just keep counting out to infinity, right?
Right.
But in this ring, when you count past the highest notch, you wrap around back to the beginning.
Like going past 12 on a clock brings you back to 1.
Very similar, but with a twist. And this is the negacyclic property. As you wrap around this specific ring, your values flip their mathematical sign. Positive becomes negative.
Oh, interesting.
Yeah, so if you push a positive signal past the boundary, it wraps around and emerges as a negative signal on the other side. This creates a deeply stable, bounded environment.
Stable because it can't just spiral out of control.
Exactly. It means numbers can never explode to infinity, and they never require infinite decimal places to represent a relationship. The relationships are encoded in how the numbers interfere with each other as they wrap around.
Okay, so it's this closed loop where values flip signs as they pass the boundary. But how does an AI actually do its thinking in this space? Because standard AI compares a query like what it's looking for to a key what information it already has, using massive dot products to see how well they match.
Right, and those attention dot products are basically the main reason AI uses so much electricity today. It's heavy math. But in this architecture, both the queries and the keys are mapped into this exact integer ring.
Okay.
Because they exist in this bounded negacyclic space, the architecture replaces those heavy matrix dot products with polynomial multiplications, specifically negacyclic polynomial convolution.
Convolution. So instead of taking a massive grid and multiplying it by another massive grid, what are we actually doing physically?
We are taking two polynomials, you can think of them as two complex wave patterns, and sliding them past each other to see where their shapes align.
Okay, wave patterns sliding past each other.
Yeah, and because of the negacyclic ring, this sliding and aligning can be computed using the number theoretic transform, or the NTT.
Ah, the NTT. The sources mention the NTT heavily. They claim it completely removes the need for 128-bit arithmetic processors.
It absolutely does. The NTT is the secret to making this fast. It takes these complex, wrapping polynomial convolutions and mathematically translates them into highly compact, point-wise multiplications.
Point-wise meaning?
Imagine instead of having to cross-multiply every single intersection in a giant grid, the NTT transforms the data so you can just line up two strings of numbers and multiply them straight across, one-to-one, in a single pass.
Oh, wow. So you are collapsing a multidimensional matrix problem into a linear one-to-one multiplication. And because it's exact integer math, it fits perfectly into standard 64-bit hardware.
Or even 32-bit hardware in some cases. There are no fuzzy decimals to keep track of, there are no rounding errors compounding over billions of operations, and there's absolutely no need for massive specialized silicon just to handle the overflow.
So the negacyclic ring acts as a perfectly stable memory substrate where exact algebraic structures they replace continuous fuzzy probability.
Exactly.
Okay, that covers the arena where the math happens, but there is a geometric principle driving how things move inside that arena, and the sources call it the three-gap theorem. This is framed as the core engine of the entire system, right?
It is the mathematical heartbeat of the architecture.
Yeah.
And to understand its power, we have to look at the concept of discrepancy, or clustering.
Clustering. Let's build an analogy here. I'm imagining that circular running track again.
Sure.
If I decide to run laps around this track, but I take a highly specific, irrational stride length-like, a stride that cannot be written as a simple fraction of the track's total length, my footprints are going to start scattering all over the track as I run lap after lap.
Yes, because your stride is irrational, you will literally never step in the exact same spot twice. Your footprints will slowly fill in the entire circle.
But here's what the three-gap theorem states, and it feels almost counterintuitive to me. No matter how many steps I take, 100, a million, a billion, if I freeze time and measure the physical distance along the track between any two adjacent footprints,
Yeah.
I will only ever find a maximum of 3 distinct gap lengths. Never 4 different gap sizes, never 50, just 3 specific distances separating every single footprint on that entire track.
It is a profound geometric truth. You would expect chaos, right?
Completely.
You would expect a massive, random assortment of distances between footprints. But the mathematics of irrational rotation dictates that the spacing always collapses into, at most, 3 distinct gaps.
Okay, that is mathematically beautiful, I admit. But how does an AI architecture actually use that?
By weaponizing it to achieve what the sources call 3-gap optimality.
Weaponizing math, I love it.
Well, think about it. If you are an engineer designing a system, your biggest enemy is clustering. If you're distributing data across memory or assigning tasks to processors, you want things spread out as evenly as possible.
Yeah.
You don't want massive empty gaps, and you don't want crowded clusters where everything bottlenecks.
Normally we just use random number generators to spread things out, right?
We do, but randomness is inherently clumpy.
Clumsy.
Yeah. Think about flipping a coin. If you flip it 1,000 times, you are guaranteed to get streaks of 5, 6, or 7 heads in a row. Randomness creates clusters. So if you use random hashing to place data into computer's memory, some sectors will be packed full, causing bottlenecks, while other sectors sit completely empty.
So we need a way to distribute data that is perfectly fair, deeply unpredictable, but entirely free of clusters.
And that is exactly what the 3-gap theorem provides, if you choose the absolute best irrational number for your stride.
The best irrational number.
Yeah, there's a mathematical hierarchy of irrational numbers ranked by how badly they approximate simple fractions. The number that is the absolute hardest to approximate, the quote-unquote most irrational number in existence, is the golden ratio.
The golden ratio, the exact same ratio that dictates the spiral of a galaxy or the arrangement of seeds in a sunflower.
Or classical architecture, yeah. It shows up in nature, precisely because nature is trying to optimize packing without overlapping. If a plant grows its leaves using the golden ratio as a rotation angle, it guarantees that new leaves minimally shade the older leaves.
That is fascinating.
And the architecture takes that exact biological principle and applies it to computer science. By using the golden ratio for rotations within the negacyclic ring, the system uniquely minimizes clustering. It achieves the deepest possible avoidance of bottlenecks.
The sources refer to this as achieving bounded discrepancy.
Right. Bounded discrepancy means there is a strict mathematical guarantee on how uneven the distribution can get. By replacing clumpy pseudo-random number generators with deterministic golden ratio spacing, the architecture guarantees mathematically optimal fairness. It completely eliminates the clumps, whether it's placing data in memory or routing signals across a chip.
Okay, so we have our foundational substrate, we have negacyclic rings handling exact polynomial math without floating point bloat. And we have the golden ratio, via the 3-gap theorem, guaranteeing perfect, uniform distribution without the clustering of randomness.
Exactly.
But building a better foundation is different from building the house. How does this beautiful math actually run an artificial intelligence? Because modern AI is built on the transformer architecture.
And this brings us to the core mechanism, the prime power transformer, or the PPT. The sources outline a roadmap to completely replace standard transformer math with exact algebraic equivalence.
Looking at the documents, they emphasize a 13-step exact substitution table. The claim is that they have gone through the standard forward pass of a transformer, literally every mathematical operation from the moment a word enters the model to the moment a prediction comes out, and swapped it for these exact ring operations.
Every single layer. The embedding lookups, the normalization, the positional encodings, the query key value attention mechanism, the feed-forward networks, they have systematically dismantled the continuous operations and replaced them with discrete prime algebra.
I have to pause here because the claim they make next defies common sense to me. They state that by running this entirely different math polynomial rings, golden ratio rotations, prime factorizations, they achieve bit-identical results to standard floating point models. They specifically cite matching the outputs of a model called Gemma 1B.
Bit identical, not just similar, not statistically indistinguishable.
Wait, really?
Really, if you give the standard power-hungry floating point model a prompt, and you give the exact same prompt to the prime power transformer, the output text is identical down to the binary level.
How is that logically possible? I mean, if I translate a novel from English to French and back to English, the words change. If you translate a continuous fuzzy neural network into a rigid, discrete algebraic ring, how do you get the exact same answer?
Because it's not a translation of approximation. It's a mapping of isomorphisms.
Isomorphic.
Right. The 13-step substitution uses exact prime algebraic mappings. They aren't trying to estimate the floating point math. They found the deeper algebraic structure that the floating point math was clumsily trying to approximate in the first place, and they just execute the logic natively in that structure.
That's incredible.
Yeah, the bit-identical nature basically proves that the continuous decimals were never actually necessary for the AI's logic. They were just an artifact of how we traditionally built the hardware.
That is a staggering realization. It means the entire industry is burning gigawatts of power computing trailing decimals that the underlying logic doesn't even strictly require.
Exactly.
Okay, let's dig into the mechanics of how these substitutions actually work, starting with the heart of a transformer, the attention heads. In standard AI, you have query, key, and value projections. How does the prime power transformer reconstruct that?
Well, standard models use dozens of independent attention heads. Every single head takes the input data and independently calculates its own query matrix, its own key matrix, and its own value matrix. It's incredibly redundant and burns massive compute.
Right.
But the PPT introduces something called twin prime heads.
Twin primes. So prime numbers that are separated by a gap of exactly 2, like 11 and 13 or 41 and 43?
Correct. The architecture pairs the attention heads up mathematically based on twin prime indices. So if head 17 and head 19 form a twin prime pair, they no longer operate in isolation. They share their query and key weights.
Oh, I see.
Yeah, they compute the attention map together cooperatively.
But wait, if they share the query and key, why aren't they just one big head?
Because they maintain completely independent value weights. They look at the data together, they figure out what is important together using the shared Q and K math, but they extract different insights, different values from that shared attention.
That makes a lot of sense. It cuts the query and key computation in half for those paired heads. But the sources suggest the real magic of this twin prime setup isn't just saving compute. It's about something called spinor reconstruction.
This is where we see the negacyclic ring really flex its muscles. In a standard model, once the attention mechanism figures out what parts of the sentence are important, it has to calculate the final values. To do this, standard architectures physically materialize a massive intermediate dense tensor in the computer's memory.
Meaning it has to generate a gigantic grid of temporary decimal numbers, write them all to the RAM, read them all back out, perform the final math, and then throw the temporary grid away.
Exactly. It's a massive bottleneck known as memory bandwidth. The processor is just constantly waiting on the RAM to store and retrieve these temporary scratch pads.
Right.
But the prime power transformer uses spinal reconstruction to bypass this completely. Because the paired heads share the Q and K math natively in the negacyclic ring, the system can assemble the combined value data directly from what they call anchor coefficients.
Anchor coefficients. These are the fundamental mathematical roots inside that wrapping ring we talked about?
Yes. Instead of building the giant temporary grid, the math allows the system to reach directly into the ring and pull out the exact structural essence of the answer. It synthesizes a highly compressed 63-byte spinor block, and this 63-byte block contains all the necessary value information for that attention pass.
So it skips the intermediate scratch pad entirely.
Completely. It builds the microscopic 63-byte answer directly from the paired head's anchor coefficients without ever materializing the dense tensor.
Let me try to visualize this. Standard AI is like wanting a specific color of paint, but the only way to get it is to manufacture 10,000 gallons of different colors, mix them all in a massive swimming pool, extract one tiny vial of the final color, and then drain the pool.
That's a great way to picture it.
And the PPT is like knowing the exact atomic formula of the color you want and just synthesizing the single vial directly on the desk.
That is exactly the paradigm shift, and that direct synthesis, bypassing the continuous intermediate steps, is applied to how the AI understands the order of words as well. This is what the outline calls three-step relative attention.
Right, positional embeddings, because an AI doesn't inherently read left or right. It takes in a whole block of text at once. So to understand that the dog bit the man has a fundamentally different meaning than the man bit the dog, it uses something called ropey rotary positional embeddings.
And standard rope uses continuous floating point trigonometry to calculate the relative distances between words. It relies on sines and cosines.
Okay.
It constantly calculates curves to determine that the word dog is exactly 3 spaces away from the word man. Calculating those continuous trig functions for tens of thousands of words is computationally exhausting. and it requires immense memory caches to store all those relative positions.
But the PPT eliminates the continuous trigonometry using the three-gap theorem. We hit this in the focus instructions. It says, and I'm quoting here, for each relative offset delta equals m minus n, the phase shifts at each dimension, when sorted, have at most 3 distinct gaps.
Right.
Unpack that physical process for me. What does that actually mean?
So in standard ROPE, as the distance between two words increases, the mathematical rotation applied to them moves along a smooth, continuous wave. Every tiny distance has a highly specific, unique decimal angle on that wave.
Right, lots of trailing decimals.
But the PPT applies the golden ratio rotation we discussed earlier.
The irrational stride on the track.
Yes, and because of the three-gap theorem, when you measure the phase shifts, the mathematical angles representing the distance between any two words, they do not form a smooth, infinite curve of different decimals.
Okay.
When you sort those angles modulo 2 pi, they collapse into at most 3 discrete geometric increments.
Wait, so instead of the processor having to compute, say, angle 45.123, then 45.456, then 45.789 along a smooth sine wave, it just mathematically jumps.
It collapses continuous, infinite trigonometry into a discrete combinatorial jump. The relative position rotation matrix for any offset only ever has to choose between 3 distinct increments rather than hundreds of continuous floating point values.
My pushback here is about resolution again. If you collapse a smooth curve into 3 discrete geometric jumps, don't you lose the ability to tell exactly how far apart the words are?
You would if you were mapping it onto a linear line. But because this is happening inside the multidimensional negacyclic ring, the specific combination of those 3 discrete jumps perfectly encodes the exact relative distance without needing the smooth curve.
I see.
It's kind of like replacing a sliding dimmer switch with 3 highly specific toggles that somehow still give you infinite control over the light.
And what's the practical engineering result of collapsing that trig?
Roughly 43 times memory reduction in the relative attention cache.
43 times.
Yeah. That is a staggering efficiency gain simply by swapping continuous sine waves for discrete prime math.
Which leads us to the next massive substitution, Mobius reordering and inversion. This targets the very first thing an AI does, embedding lookups. When you feed an AI a prompt, it doesn't see letters, it sees tokens.
Right.
And normally, those tokens are just arbitrary integer IDs. The word apple might be token number 500. The word banana might be token 501.
And when a standard AI sees token 500, it just performs a massive random read from its hard drive. It looks up row 500 in a giant spreadsheet to find the huge grid of decimals that represents the meaning of an apple. It's arbitrary and linear.
But the PPT indexes tokens using square-free integers.
Let's define that really quickly. A square-free integer is a number which is divisible by no perfect square other than 1.
Okay.
So the number 10 is square-free because its prime factors are 2 and 5. Neither of those are squares. But the number 12 is not square-free because it's divisible by 4, and 4 is a perfect square, 2 squared.
Okay, why would you index the English language using numbers that don't have perfect squares hiding inside them?
Because square-free integers have a unique property in number theory. They are built from perfectly distinct, non-repeating primary prime numbers. The PPT uses this structure to perform Mobius inversion.
Mobius inversion.
Right. Instead of storing one giant, heavy, isolated file for the word apple, the system reconstructs the tokens embedding dynamically using the primary prime indices that make up its square-free ID.
Let me try to make this concrete. Instead of token 500 just pointing to a locked box labeled apple, maybe the word apple is assigned a square-free ID made of the prime numbers 2, 3, and 7.
Okay.
And in this architecture, maybe 2 represents the mathematical concept of red, 3 represents fruit, and 7 represents crisp.
That is the exact semantic intuition, yes. The embedding lookup becomes combinatorial rather than a single massive read. You are combining atomic prime concepts to build complex words dynamically. And to make this incredibly fast in hardware, they use Mobius reordering.
What are they reordering?
They physically sort the data structures in the computer's memory so that the coefficients associated with square-free indices always come first. By putting them at the front of the line, the system identifies unique anchor coefficients.
Anchors again.
Yeah. These anchors carry the multiplicatively primitive information. The system never has to dig through redundant data. It grabs the atomic prime concepts instantly.
Every layer of this architecture is just about replacing brute force iteration with geometric elegance, which brings us to perhaps the most fascinating efficiency gain, the adaptive depth loop governed by Poncelet closure. This addresses how much thinking the AI actually does.
Right. So in a standard transformer, if you have a 32-layer model, every single token runs through all 32 layers. The simple word "the" gets the exact same amount of heavy mathematical processing as a highly complex word like anti-disestablishmentarianism.
Which seems terribly inefficient.
Okay.
The AI probably figures out what "the" means by layer 2. Why run it through 30 more layers?
Well, standard architectures don't have a reliable way to mathematically know when a token is done processing. But the PPT solves this dynamically using Poncelet closure.
Poncelet closure. When I look this up, I found a 19th century theorem by a French mathematician named Jean-Victor Poncelet. It's a classic geometric property about polygons inscribed inside one conic section and circumscribed around another.
That's the one.
How does a 19th century geometry theorem dictate the depth of a neural network?
We have to remember that as data moves through the layers of a neural network, you can mathematically plot that data as a geometric shape evolving in high-dimensional space. The PPT constantly monitors the activation statistics of the tokens. It monitors the shape of the data.
And it's looking for that shape to do something specific?
It's looking for the shape to close an orbit. It applies the Poncelet geometric condition to the statistics. As the token moves from layer 1 to layer 2 to layer 3, the geometric representation rotates. When that geometric shape perfectly closes upon itself, satisfying the Poncelet condition, the mathematics dictate that no further novel transformation is occurring.
So the model physically recognizes that it has achieved a state of mathematical redundancy for that specific token.
Yes, it realizes it has fully understood the token's context.
Yeah.
And when Poncelet closure is triggered, the model simply stops processing that token. It triggers layer skipping.
Adaptive depth. If the word "the" achieves Poncelet closure at layer 3, it just skips layers 4 through 32, yielding massive free compute savings.
Exactly. It dynamically optimizes the layer depth token by token, completely eliminating redundant compute while still maintaining the bit-identical accuracy of the final output.
Okay, we have completely re-engineered the processing logic. We threw out continuous matrices, we're using exact prime convolutions, we're building outputs directly from anchor coefficients, collapsing trigonometry into discrete jumps, and mathematically skipping layers.
That's the compute side, yeah.
Right. The processing bottleneck is solved, but if we are processing tokens this fast, the bottleneck immediately shifts. Where does all this data go? If our memory relies on clunky linear RAM, the processor will just sit around waiting for data to load.
This is the critical transition. Fixing the compute logic is only half the battle. If you don't rebuild the memory architecture, you hit a hard scaling wall.
And the sources detail exactly how they rebuild memory, starting with the biggest headache in modern AI, the KV cache or the context window. Everyone wants an AI that can read entire code bases or summarize a 1,000-page novel, but context windows fill up. And standard models use crude eviction policies when the memory gets full.
Right, they use FIFO first in, first out, or LRU least recently used.
Which are disastrous for maintaining long-term coherent context. If you use FIFO to summarize a novel, the moment the cache fills up, the model deletes the first chapter. By the end of the book, it literally has no memory of how the story started.
And if you use least recently used, it just deletes the boring middle chapters that it hasn't referenced in a while, leaving massive arbitrary gaps in the middle of the context window. The AI completely loses the ability to connect long-range ideas.
This is where the architecture introduces Fibonacci subsampling for KV cache eviction. This is a major focus point in the documentation. When the KV cache needs to be compressed because it's hitting a memory limit, it does not use FIFO or LRU. It keeps tokens at extremely specific mathematical positions.
The instructions give the exact formula. It keeps tokens at positions defined by the floor of k times phi times n modulo n.
Okay, unpack that formula spatially for us. How does that physical process work inside the memory?
Imagine the context window as a long thread. When the memory is full, you need to pull some tokens out to make room. The formula takes the tokens index, k, and scales it by the golden ratio, phi.
The golden ratio again.
Yes, it stretches that value across the total size of your context window, n. Finally, the modulo n part wraps that stretched value back around the thread, like winding a spool.
So it's picking positions based entirely on golden ratio rotations across the total length of the memory.
Yes, and because it uses phi, the three-gap theorem asserts its power again. It guarantees that picking positions this way maximally and uniformly covers the entire temporal context, regardless of how large and the total context window gets.
So it's not deleting a massive clump from the beginning, and it's not tearing arbitrary holes in the middle. It is perfectly evenly thinning out the memory across the entire timeline of the conversation.
It gives you bounded discrepancy on the temporal axis. Your memory degrades gracefully. You lose strict high-resolution detail of every single word, but you perfectly preserve the overall shape, structure, and pacing of the entire document.
That's brilliant.
And, crucially, the documentation notes this pairs naturally with the VHT2 and spinor compression already in the framework.
Because you replace random subsampling with golden ratio subsampling, the bounded discrepancy on the temporal axis matches what they achieve on the frequency axis with the negacyclic rings.
Exactly. The geometry of the memory compression matches the geometry of the compute logic perfectly.
That handles the short-term context window. But what about long-term storage? If this system is crawling massive data sets, where are the permanent concepts stored? The sources introduce holographic slabs and algebraic resonance memory, or ARM.
This brings us back to the negacyclic ring acting as a stable memory substrate. Standard memory stores data linearly.
Yeah.
One piece of data goes into one memory slot. If you want to store a billion facts, you need a billion slots.
Right.
ARM completely discards linear storage in favor of holographic reduced representations, or HRR, operating within that cyclotomic ring.
Let's focus on the word holographic, because if I take a traditional photograph and tear it in half, I lose half the image. But if I take a holographic plate and shatter it, every single tiny shard still contains a faint, complete image of the entire original object. The information is distributed globally across the medium.
That is the exact operating principle of ARM. The system uses algebraic resonance to store many different key-value memory bindings compactly inside a single 63-byte negacyclic ring element.
Wait, they are storing multiple distinct memories into the exact same physical 63 bytes of space. How?
Through polynomial ring addition. Imagine dropping a pebble into a calm pond. It creates a specific wave pattern. If you drop a second pebble nearby, its waves interfere with the first.
Okay, I'm picturing it.
In a standard computer, writing new data over old data destroys the old data. But in the exact math of the negacyclic ring, these memory polynomials superimpose on top of each other. Because the ring is mathematically exact, you can later isolate and extract the specific wave pattern of the first pebble, even though the surface of the pond looks chaotic.
But the laws of information theory say you cannot fit infinite data into a finite space. There has to be a physical limit to how many memories you can stack into 63 bytes before the waves just turn into pure static.
You are correct, and the architecture defines this limit as memory degradation. The recall noise scales mathematically. It scales as big O of the square root of k, where k is the number of items bound into the slab.
So as k goes up, as you bind more and more memories into the same 63 bytes, the noise floor rises.
Exactly. If you bind too many items, the interference overwhelms the signal, the algebraic resonance fails, and the recall capacity degrades into fuzziness. To maximize capacity, to keep that noise floor as low as possible for as long as possible, you need the memory keys to be mutually near orthogonal under circular convolution.
Let's break that down. Orthogonal keys. If my keys are too similar, they clash. Like if I try to store the concept of apple and the concept of pear using wave patterns that are almost identical, they will heavily interfere and corrupt each other in the slab.
Right.
Orthogonal means the patterns are as different from each other as mathematically possible, minimizing interference.
Yes. In standard computing, generating those perfectly non-interfering orthogonal keys is incredibly computationally expensive. Systems usually rely on complex random projections or heavy linear algebra like the Gram-Schmidt process just to forge a usable key.
But the focus instructions point out a brilliant shortcut for ARM key generation. They don't use Gram-Schmidt, they don't use random projections, they use deterministic generation from our old friend, the golden ratio, k times phi.
By spacing the mathematical phases in the ring using golden ratio increments, they achieve mutually near orthogonal keys deterministically. The math naturally provides perfectly spaced, non-interfering wave patterns without any expensive generation overhead.
That's so elegant.
And the documents state this materially improves the capacity curve, allowing them to push far past previous limits of how many memories can be stacked in a single slab.
It's just relentlessly efficient. Every time there's a complex, heavy operation in traditional computing, this architecture replaces it with a deterministic geometric property of the golden ratio.
That's the core philosophy, yes.
Yeah. But there is one final piece of the memory puzzle. If you are scraping the internet for data, you're going to encounter the exact same information millions of times. You don't want to store a million copies of the same Wikipedia article, even if you compress them perfectly into holographic slabs. How does the system know if a new piece of data is actually semantically novel?
Deduplication at a global scale is a massive challenge. To solve this, the architecture uses something called the Friedman sieve, which relies on a specific data structure, KSTE, or Night-Spiner tree encoding.
Night-Spiner tree encoding, what does that actually look like?
When the system ingests new content, it maps the semantic meaning of that content into a mathematical tree consisting of up to 60 nodes. It turns a paragraph of text into a rigid structural geometric tree representing its core concepts.
Okay, so every piece of knowledge is a 60-node tree.
The Friedman sieve's job is to measure semantic novelty by comparing these trees. It filters redundant data by checking if a new tree is mathematically dominated by a tree that is already stored in the system.
Dominated meaning. If I feed the system an article about how water is composed of hydrogen and oxygen, it builds a tree. If I later feed it a slightly different article that basically says the exact same thing, the new tree will literally fit inside the structure of the old tree.
Precisely. If the structure is contained within an existing tree, the system recognizes it is not semantically novel. It possesses no new structural knowledge. The data is simply discarded.
But hold on. Comparing millions of complex 60-node mathematical trees against every other tree in a global database sounds computationally agonizing. The latency would be massive.
And it would be if they compared the full trees. But they use a tier 0 pre-filter. To quickly check for novelty, the system generates multi-set signatures for the trees, and the novelty detection is executed using a single 64-bit constant time subtract with borrow operation.
A subtract with borrow operation. I know that is a deeply fundamental hardware instruction. Break down how that actually measures novelty.
In the processor's ALU, the arithmetic logic unit subtract with borrow is one of the most basic things a chip can do. The multi-set signatures are formatted sequentially. The chip takes the signature of the new tree and subtracts the signature of the old tree.
Okay.
If the new tree is completely contained within the old tree, the subtraction will process cleanly. But if the new tree has even one piece of novel structural data, the subtraction will mathematically require the processor to borrow a bit from an adjacent column to complete the calculation.
And the processor physically flags that borrow event?
Yes. The system just watches the hardware flag. If the flag triggers, the data is novel. If it doesn't, the data is redundant. It takes literally one single ALU instruction on a standard chip, a single microscopic tick of the processor clock to filter massive amounts of semantic data.
That is absolutely breathtaking. They mapped high-level semantic language comprehension all the way down to a single binary hardware flag.
It's incredible engineering.
Okay, let's take a macro view. We've completely rebuilt the silicon processing with prime polynomial rings. We've rebuilt the memory with golden ratio eviction, holographic slabs, and the Friedman sieve. But the Shannon-Prine lattice isn't just a chip architecture. The exact same mathematical principles we just explored at the microscopic level are used to organize a global network of distributed computers.
This is where the architecture attempts to scale to the world. If you are building a planetary network of computers sharing and processing these AI workloads, you need a distributed hash table, or DHT. You need a map to know which computer holds which specific holographic slab of data.
Standard global networks like torrents or standard blockchains use arbitrary cryptographic hashes. It's essentially random. A computer in Tokyo might hold piece A, and a computer in London holds piece B with absolutely no logical relationship.
Right.
But the lattice uses a two-axis address scheme. And looking at the focus instructions, the two axes are prime factorization and the Fibonacci sequence.
Let's dissect how this hierarchical space works, starting with the first axis, semantic adjacency. This relies on the prime factor coordinate space. In this network, the physical routing of data is tied to its meaning. Related content physically lives at nearby prime indices.
Let's build an analogy here. Imagine a massive, globally distributed library. The prime numbers dictate the specific genre or subject of the information. All the nodes holding data about quantum physics are clustered mathematically around a specific set of prime coordinates. If I'm an AI looking for quantum physics data, I navigate the prime axis to find that semantic neighborhood.
That analogy perfectly captures semantic adjacency, but it immediately highlights a massive networking flaw. Load balancing.
Word balancing, yeah.
If there is a sudden global breakthrough in quantum physics and billions of users suddenly query that specific semantic concept, all traffic rushes to that one prime coordinate neighborhood. The nodes holding that data will be instantly overwhelmed and crash, while nodes holding data on ancient pottery sit completely idle.
Right, the popular node problem. They would get crushed by the compute requests. So how do they balance the load without losing the semantic grouping?
That is the exact purpose of the second axis, load adjacency. To prevent overwhelming those semantic nodes, the network applies Fibonacci hashing strictly on top of the prime factorization.
Fibonacci hashing. So we are bringing the golden ratio back to scatter the load.
Yes. It creates a hierarchical Fibonacci of prime address space. The prime factor coordinates capture the semantic meaning, grouping the data, but the Fibonacci hash captures the computational load, distributing those requests uniformly within each prime slab.
Going back to the library analogy, the prime axis puts all the quantum physics books in one specific massive wing of the library.
Yeah.
But the Fibonacci axis ensures that the thousands of readers trying to read those books are mathematically perfectly spaced out across hundreds of different identical copies held by different librarians within that wing.
Exactly.
No one bumps elbows, and every single node handles the exact same amount of work.
And crucially, both axes have provable distribution properties. Routing within the global lattice becomes simple and incredibly elegant. You navigate the prime axis for semantics, and you navigate the Fibonacci axis for load.
Okay, the routing is mathematically perfect. But what about security? This is a distributed network. If I'm asking a random node in Tokyo to process a highly sensitive, proprietary AI workload for my company, what stops the owner of that node from just intercepting the data and stealing my AI's thoughts?
That vulnerability is solved by dual prime CRT sharding. CRT stands for the Chinese remainder theorem, an ancient mathematical concept. The lattice uses this to achieve information theoretic security.
Information theoretic security is the absolute highest standard in cryptography. It means the security doesn't rely on the encryption just being too hard to guess with current computers. It means it is mathematically impossible to decipher the data, even if the attacker has infinite computing power and infinite time. How do they pull that off on a public network?
It happens during the number theoretic transform phase we discussed at the very beginning. The computations are split sharded across two co-prime 30-bit Proth primes. The protocol hardcodes two specific constants. Let's just call them Q1 and Q2.
Why does it matter that they are coprime?
Coprime means they share absolutely no common mathematical factors other than one. They're completely mathematically alien to each other. When a sensitive workload is sent across the global network, it is split. Node A is given the data encoded modulo Q1. Node B, halfway across the world, is given the data encoded modulo Q2.
And because the times are coprime, knowing the Q1 data gives you absolutely zero mathematical clues about the Q2 data. It's like having half of a physical key where the two halves are made of completely different multidimensional geometry.
Exactly. Neither shard is mathematically useful on its own. If a malicious node intercepts the Q1 shard, what they possess is information theoretically useless. It looks entirely like random, chaotic noise. To extract any usable information whatsoever, you strictly require both shards simultaneously.
And when the two honest nodes finish their separate processing, how do they bring the answer back together?
Through Garner reconstruction. The Chinese remainder theorem guarantees that you can merge those two distinct coprime moduli back together to perfectly reconstruct the final exact output. It means you could distribute massive, sensitive AI workloads across completely untrusted computers, and it is mathematically impossible for them to steal the data.
We have perfect routing, perfect load balancing, and unbreakable security. But a global decentralized network needs a way to agree on the state of the network. It needs consensus. The sources outline a blockchain ledger that tracks work tokens for nodes, providing compute power, and discovery tokens for nodes that find novel semantic trees.
Which brings us to the final massive inefficiency of modern systems: validator selection in blockchains. To agree on the ledger, the network has to constantly choose which node gets to validate the next block of transactions.
The standard approach for modern blockchains is stake-weighted random selection. The network looks at who has staked the most tokens and then rolls a massive digital die to randomly pick a winner. But to prove that the die roll was fair, they have to use incredibly complex cryptography, like a VRF, a verifiable random function.
Which requires a massive expenditure of energy and compute just to generate a fair random number. It requires constant network communication to agree on the beacon, and if a node fails to cooperate with the random beacon, they have to be financially punished or slashed. It is a chaotic, heavy process that contradicts the extreme efficiency of the rest of the lattice.
So if they aren't using a random VRF beacon to pick validators, what is the breakthrough here?
They eliminate randomness entirely. They replace it with golden ratio rotation.
Phi makes its final appearance.
It does. Instead of rolling dice, the network simply steps through the set of all validators by continuous increments of the golden ratio.
I need to push back here. The whole point of validator selection is that it has to be unpredictable. If you are just moving by a fixed, predictable increment of phi, can a malicious actor map out exactly when they will be chosen and game the system? How does stepping by a fixed number provide fairness and security?
Because of the three-gap theorem and bounded discrepancy, imagine the entire set of validators mapped onto the edge of a circle. The stake weighting, how many tokens a node is locked up, is baked into the physical length of their interval on that circle. A node with a massive stake gets a large slice of the pie. A small node gets a tiny sliver.
Okay, I have my circle of validators.
Now draw a pointer starting at the top and advance it around the circle by the golden ratio. Because phi is the most irrational number, that pointer will jump erratically around the circle, never repeating the exact same sequence. It looks incredibly chaotic, but bounded discrepancy guarantees mathematically optimal fairness.
Because it uniquely minimizes clustering.
Yes. It touches every single interval perfectly proportionally to its size over time, without ever clustering on one validator. It achieves provable fairness without needing a random beacon at all.
The consensus is achieved entirely through the deterministic geometry of the golden ratio.
Which results in vastly cheaper consensus. There are no heavy cryptographic rounds needed to agree on a random number. Because the rotation is deterministic, any node can instantly mathematically verify whose turn it is. There is no need for complex slashing mechanics for beacon non-cooperation, because there is no beacon. The network achieves perfect, fair agreement natively.
When we take a step back and look at the entire Shannon prime lattice, the sheer scope of the engineering is staggering.
It really represents a completely unified theory of computing infrastructure.
Just think about the layers we have unpacked today. At the microscopic silicon processing layer, they execute a 13-step exact algebraic substitution, throwing out power-hungry floating-point matrices for exact prime polynomial rings and skipping layers dynamically with Poncelet closure. At the memory layer, they manage the context window with Fibonacci subsampling and store concepts compactly in holographic slabs using algebraic resonance.
And at the macro scale, at the global network layer, they route that data using a hierarchical two-axis prime and Fibonacci address space. And finally, at the blockchain consensus layer, they organize the entire global state using golden ratio rotation.
The profound revelation here is that it is all the exact same mathematical object reappearing at different scales, from the arithmetic logic unit inside a microchip, to the memory cache, to a global planetary network of peers.
It is fractal elegance. It is like discovering that the blueprint used to build a skyscraper is the exact same mathematical blueprint used to construct the atoms in the steel.
And the tangible impact of that uniformity is ultimate efficiency. Bit-identical AI results, achieving the exact same logical output, but with a fraction of the compute power, a fraction of the memory bandwidth, and information theoretic security baked directly into the physical mathematics of the system.
It is not a software optimization. It is a fundamental paradigm shift away from brute force engineering.
And that is why this architectural shift matters so deeply right now. We live in a world terrified of hardware limits, of the staggering economic and environmental costs of energy, of the sheer thermodynamic wall we are hitting as we try to scale AI. The current industry strategy is just trying to build bigger, hotter bulldozers. But what we've seen today proves that rethinking the absolute mathematical foundations, abandoning sloppy continuous decimals for deterministic, beautifully distributed number theory, is how we actually build the future.
The path forward isn't more power, it is deeper geometry.
I want to leave you with a final thought to mull over. If an imaginary quadratic field, negacyclic rings, and the simple geometry of the golden ratio can completely replace the heavy lifting of modern artificial intelligence and coordinate global network consensus, look around you. Look at the complex systems we interact with every single day. Traffic grids, global supply chains, financial markets, logistical routing. What other chaotic, energy-burning, inefficient systems in our society are just waiting for a prime number revolution?